So again, let's recall what we have learned last week. Last week mainly is Law's law and Henry's law. So basically we have two-phase system, right? And then we have on the condition of temperature. Hello, everybody, settle down, okay? Settle down. Right, so we have temperature and pressure, and we know that if we have many species in the gas and the liquid phases, then we will have molar fractions in gas phase and the liquid phases. So you will have XA, XB, XC, and YA, YB, YC. So Law's law is that, in addition, you want to know the partial pressure of the A species in the gas phase, and also the partial pressure of B species, partial pressure of C species, etc. Okay, so first of all, if you have so many species, and then for the species which is very easy to decompose, very easy to become liquid. So in this kind of case, we use Law's law. Okay, and then we understand Law's law is that PA equal to YA times capital P equal to XA times PA star. So this is the equation you need to remember. And then in order to get PA star, you need to use equation, or you need to get PA star from table or Koch's chart, from the table, from the chart, or from the equation. Okay, so for Henry's law, this is Henry's law. Normally, this Henry's law is applied to the gases which is not easy to decompose, condensed. So we say insoluble. So, for example, if you have like carbon dioxide, you have oxygen. So normally you use Henry's law. You apply Henry's law in this two-phase system. But if you have water or like alcohol, then you use Law's law for in this system. So this is the Henry's law. The differences between Henry's law and Law's law is that this is different. This is called saturation pressure, vapor pressure, right? And this is HA. And you, in order to get HA, function of T, you need to find from the tables. Okay, so this is what we call ideal solution. So ideal solution is that normally it's ideal, and you need to use this equation to find out the molar fractions in gas liquid phase, molar fraction in gas phase, and also the partial pressure. Right. So today, I want to introduce you VLE. We call vapor liquid equilibrium calculations for the solutions that obey Law's law. In another word, is that we want to use this. We want to do the calculation for the ideal solution, because that obeys Law's law, right? So this is important. Let's recall what we have learned in the last week. Is that we start from a single component vaporization process. I hope you are familiar with these figures. This is for single component, right? So in the point C here, you have temperature and pressure, right? Temperature and pressure. Okay, for example, temperature is 20 Celsius and pressure is 760 millimeter mercury. Okay, and then you start to increase the temperature. So the heat is added slowly to the closed vessel. This is vessel, right? That contains a liquid, and the pressure is in the vessel is held constant. So the pressure keep constant at 760, but it keep on increasing the temperature from C to D. So temperature will increase. Okay, and then pressure hold constant. And this is the line from left to the right. And then what happened to the next? The next is if you keep on increasing the temperature, the liquid will become gas. So if the temperature increases until the boiling point, The boiling point of the water here is 100 Celsius at 760 millimeter mercury, right? So if we keep on increasing temperature from 20 to 100, and liquid water start to boil, and you will keep the temperature won't change at this point if you keep on increasing the temperature. So why is this called? What's this energy called? If you increasing the temperature, if you keep on giving the energy to this system, but temperature still stay in the same position. Temperature doesn't change, but the phase change. So what kind of energy is this? What we call about this energy? Latent heat, right? Latent heat. Okay, this energy latent heat. So, and then this one, in this case, from the first bubble of this appear in this liquid phase, and until all the liquid disappear. So in this stage, we call it point D. So the temperature will always at 100 Celsius. The pressure will be always on 760 millimeter mercury in this point. Okay? And then after that, if you keep on increasing, vaporization complete, heat rise the temperature of the vapor. So if this liquid water change from liquid to become vapor, and then there's no more water anymore, the temperature will start to increase, and then from D to E, from 100 to 130, 150, something like this. So this is the one, and it looks like this. And of course, at this moment, you understand the value of this vapor increased. So this is what we call single component vaporization process. Ladies and gentlemen, it's only for single component. If you have two components, the story will be different. Okay, so now let's take a look of the on the at least two components, or we call several components. So again, let's start from the very beginning. In the liquid phase, there are A, B, C, D, E, F, for example, this species, and temperature is 0. I'm sorry, temperature is, we call temperature 0. Okay, it's certain temperature, it's not 0 Celsius. Okay, and then so liquid temperature rise until a temperature is reached at which the first bubble of the vapor form. So if we keep on increasing the temperature in this system, and then we will find, eventually we will find something, the liquid become vapor, right? So at this moment, if we keep on increasing the temperature in this system, let's say temperature 1, and then at this moment, the first bubble come out. And this is what we call bubble point. The first bubble come out. And at this moment, I want to ask you, what is the composition of this, of A, B, C, D in this bubble? Can you tell me? Because what we want to know is that we already know the molar fraction of A, B, C, D in the liquid phase. But when we have the first bubble, do you know the composition, the molar fraction of A, B, C, D in this bubble? How do you calculate this bubble? How do you calculate this? That's what we want to know. Okay? Right, and then, of course, at this moment, we keep the pressure at a constant from here to here. Okay, like the previous page. So if a liquid is a mixture, A, B, C, D, for example, the vapor generated generally will have a composition, A, YA, YB, YC, YD, different from that of liquid. Why YA and YB, YC, YD will different from XA, XB, XD? Because they have different volatility, right? Water and alcohol, they have different volatility. So that's why the composition in this bubble will different from the composition in the liquid. Okay? And then if we keep on increasing the temperature, so as the vaporization proceeds, the composition of the remaining liquid continuously change. Okay? And then hence, so does its vaporization temperature. So if we keep on increasing the temperature, you will have more bubbles. That means you have more mass, or you have more species in the gas phase. So at this moment, you have a temperature 2, let's say temperature 2. Then you will have different composition in the liquid phase and different composition in the gas phase. Let's say YA prime, YB prime, YC prime, and YD prime. Okay, and the molar fraction in liquid phase will also change. Let's say XA prime, XCB prime, XC prime, and XD prime. Okay, again, once you increase the temperature more from temperature 2 to temperature 3, for example, and it become all the gas, all the liquid phase vaporized. So we call Y double prime A, Y double prime B, Y double prime C, Y double prime D, something like this. So the interesting thing is that, can you tell me this composition in different temperature? So the composition and the temperature both changed. Okay, so this is important point. Right, so vice versa. How about condensation process? Condensation process is similar phenomena occur if a mixture of the vapors is subjected to a condensation process at a constant pressure. So for example, there's no gas, there's no liquid in this system. Let's say A, B, C, D. If we decrease the temperature, for example, the composition of this system is YA, YB, YC, YD at temperatures 3. Okay, temperature number 3. If we decrease the temperature, okay, at some temperature, the first drop of the liquid formed, and thereafter the composition of the vapor and the condensation temperature both changed. So what happens if we reduce the temperature? The first drop of the water come out, right? So this is what we call this droplet. What we call is what? Dew point. Dew point. Remember dew point? We introduced this to you before. Dew point. Okay, and at this moment, I want you to find out the composition of this droplet, A, B, C, D, or the molar fraction of A species, B species, C species, and D species in this droplet. Okay, again, we keep the pressure as a constant. So if we decrease the temperature more, then we will have more liquid formed, right? Okay. So let's say temperature 1, and we have different composition in liquid phase and different composition in gas phase. Okay. Right. So I think this is very likely to be in your final exam paper. So please pay attention to this topic. So now we want to introduce you bubble point and dew point. So you have bubble point. Just now we talked to a bubble point means the first bubble come out. That's why we call bubble point. And at that time, the temperature is called bubble point temperature. At that time, the pressure is called bubble point pressure. Again, the same as the dew point temperature and dew point pressure. Okay, so you can tune the temperature and pressure to get the composition, or you can have the different. You can predict, or you can design the composition at gas phase and the liquid phase, and we got the temperature at that time, the temperature and pressure. Okay. So what is the dew point and bubble point temperature? The bubble point temperature is that we use T sub BP. BP stands for bubble point. Okay, so when a liquid is heated slowly at constant pressure, the temperature at which the first vapor bubble form is the bubble point temperature of liquid at a given pressure. So I hope you still remember this. I just give you an example. If you have this and I decrease the temperature, I increase the temperature, the first bubble form, right? So this is what we call bubble point temperature because you increase temperature. Okay, and how about dew point temperature? Dew point the same, right? So dew point temperature is that there's no water, there's no liquid, and that decrease the temperature. So you get the first bubble. You get the first droplet. So this is what we call dew point temperature. And dew point temperature is TdP. D stands for dew, right? P stands for point. Okay, and we want to know the temperature at this moment. And this temperature is called dew point temperature. So of course, we cannot tune temperature and pressure at the same time. We have to keep one factor as a constant. So at this moment, when we talk about dew point and the bubble point temperature, we always keep the pressure as a constant. Okay, so this is important, constant pressure. So how about constant, how about dew point pressure and dew point, how about dew point pressure and bubble point pressure? That means we keep the temperature as a constant, okay? So how are we going to calculate the dew point temperature and bubble point temperature? So let's focus on this first. To calculate bubble point and dew point temperature can be a complex text for an arbitrary mixture of the components. It's difficult, but if we regard this fluid as an ideal solution, then we can use Law's law and Henry's law to solve this problem. So if the liquid behaves as an ideal solution, one for which Law's law or Henry's law is obeyed for all the components. For example, H2O use Law's law, CO2 use Henry's law, oxygen use Henry's law, CH3OH use Law's law, right? Okay, and gas can also be considered ideal. The calculations are relatively straightforward. So, you know, in this lecture, in this course, we only talk about ideal or easy one. So we use Law's law and Henry's law to calculate bubble point and dew point. It's not good answer, but it's a your answer will be close enough to the real answer. Okay, when you using the complex calculation. Okay, so it's important to realize that now you are using an easy way to solve the problem using ideal gas and ideal solution. So we use Law's law and Henry's law. Okay, so how about bubble point and dew point pressure? I just told you that bubble point pressure is the definition of first drop, and the dew point is the first droplet, right? So again, it's constant temperature. Right, so now let's move to the how to do the calculation of the bubble point temperature and the pressure calculation. So the bubble point temperature is, you assume you have all the water, all the liquids, right? And if we talk about bubble point temperature, that means we keep the pressure as a constant. And then you have A, B, C, D, something like this. And if the mixture is heated as a constant pressure P to its bubble point temperature, the further addition of a slight amount of the heat will lead to the formation of vapor phase. So that means you will have what? You will have the first bubble. So if you keep on increasing the temperature, and then you will have a first bubble, and you will have the composition or molar fraction of the species in the gas phase in this bubble. And I write down the unknown in red color. So these are the unknown, and these are the knowns. Why? Because this is the initial condition. Initial condition, you must realize the composition of the molar fraction of the A, B, C, D species in the liquid phase. So this temperature is unknown. Molar fractions in gas phase is unknown, are unknown. Okay? So how are you going to find out this? As I told you, we regard this as an ideal gas and ideal solution. So we use Law's law and Henry's law. And Law's law is this one, right? Okay? So you understand this? And how are we going to get this vapor pressure at bubble point? If you know the temperature, then you find out from the book, right? So the total pressure will be what? This is total pressure. This is none, right? Because we keep a constant. This is initial condition. So we know the initial pressure and we know the initial molar fraction. So the initial pressure will be the partial pressure. You put all the partial pressure together. The partial pressure together is what? Is this one. This is Dalton's law, right? So you put this together. And if you know this, then you replace to this. So this will be like this because Xi is none, right? Because it's in the liquid phase. So you will become like this. So total pressure will become like this equation. Okay? So when you do the calculation, important thing for you to know that the bubble point temperature is you have to add up all the partial pressure first to become total pressure. And you use Law's law as the equation. Okay? So to know the composition of the vapor phase, Yi from the TBP. So now you know that the total pressure is the partial pressure of A, partial pressure of B, partial pressure of D, C, and D. And then follow the Law's law, you can have the equation like this. And then what? So the bubble temperature may be calculated by trial and error as the value of the TBP that satisfies the equation. So the important thing is you have unknown here, right? And this is what you want to know. But can you get this? How do you get this point? So how can you get this one? Vapor pressure of A, vapor pressure of B. We use trial and error. You know that the total pressure you already know. So this is known. And you have to make this equation become 0. Right? You have to make this equation become 0. So to do the TBP, and if you find out, if you assume the temperature is 80, then you can find out the vapor pressure of A at 80 Celsius. And this is 80. This is vapor pressure of B in 80 Celsius. Vapor pressure of C in 80 Celsius. And then minus P. P is none, right? And equal to 0. So you use trial and error. You might don't understand what I'm talking about, but I will have an example for you to practice. And you need to practice that example because very likely that will show up in your final exam paper. So important thing is that you have to assume bubble point and to get this. So how are you going to, if you assume the bubble point is 80, how are you going to get the vapor pressure? Tell me. From the equation, right? From the chart or from the table. So in our textbook, I will give you Anton equation. Anton equation is an empirical equation. So you just find out A parameter A, parameter B, parameter C. Okay? So if you assume a TB, no, and you get this vapor pressure from equation, chart, or table. And this function will become 0. So you use trial and error to get the answer. So, and then once you get this, once you find out this, and then you know the temperature, then how are you going to get the partial pressure? Because Dalton's law, right? Dalton's law. Pi equal to Xi Pi star. And then you can get Law's law. You can get the Law's law. Oh, sorry, this is Dalton's law. Dalton's law. Okay? So this is what you want to know. temperature, molar fraction, and a partial pressure. So you might say, well, so next one is bubble pressure. So this one is bubble. This one is bubble point temperature, right? And the next one is bubble point pressure. Bubble point pressure is we keep the temperature as constant, right? And then we want to know where is the pressure the first bubble will come out. You might say, well, Professor, why we need to learn this? When you have a soda, when you have a sparkling drink, and then you need to calculate what's the pressure inside in order not to let the first bubble come out, right? So you need to know what's the pressure you need to feel into this container in order not to let the bubble come out. Because when you open this, the pressure drop. The pressure drop, the bubble will come out, right? Then you will have a nice drink. But when you sell this as a product, engineer need to design the pressure. Okay, so this is one of the example. So the bubble point pressure is that we keep the temperature as a constant, and then we know the composition in the liquid phase. So the pressure at which the first vapor form when a liquid is decompressed. Decompressed means what? Decrease the pressure, right? And we keep the temperature as a constant. It's bubble point pressure of the liquid at a given temperature. So if we start to open this can gradually, you will see that the temperature or the pressure will decrease, right? So decrease the temperature, decrease the pressure, and eventually the bubble will come out. So this is the first bubble. So either increase the temperature or decrease the pressure. Okay, you will get the bubble point pressure, or you will get a bubble point temperature. Okay, and again, at this moment, you want to know the molar fraction of this bubble, and you want to know what is the bubble point pressure. Now, how are you going to calculate this? This is for a specified temperature. Bubble point can be determined by what? Again, determined by total pressure. I just told you that in order to get the bubble point pressure or temperature, you had to use the total pressure equal to the partial pressure. Okay, and if you get a partial pressure, and this is Laws law. Laws law, right? And you put the Laws law, and because you know the temperature, so you know this. Right? Because you know the temperature, you know this vapor pressure. And because this XA, XB is known, because liquid phase, so immediately you will achieve bubble point pressure, the total pressure. So you can calculate this easily, as long as you know the composition of the soda water, okay, of the salt or sugar, something like this. So gas phase molar fraction, Y can be expressed as what? So what if you know the pressure, the bubble point pressure, what's the next you want to know? Molar fraction, right? Molar fraction. So how are you going to get the molar fraction? The molar fraction is what? Is the partial pressure equal to what? Molar fraction of in a gas phase times total pressure. So once you know this, and you don't know, right? Okay. And then you will notice this. You know this, and you know this, and you know this. So you know this. Let me say this again. You know to get yi, right? This is Dalton's law, and this is what? This is Laws law. So yi is unknown. Xi here, right? Pi star function of t is what? Because you know the constant pressure, constant temperature, right? You know the temperature here. So you know you put a t here, you get this by equation, table or chart. And B bubble point pressure, you just get the answer from here. So you know this, so you will know this. Okay? Please practice this by yourself. Okay, so you achieve Yi. So if you achieve Yi, I want to ask you, what is the partial pressure? If you achieve Yi, you know the bubble point pressure and you know the partial pressure, I. Okay? So what I want to tell you here is that when you're talking about bubble point, you also remember you have to use an equation which is total pressure equal to the partial pressure A plus partial pressure B plus partial pressure C plus partial pressure D, etc., etc. And then in order to get a bubble point temperature, you need to try and error to get the bubble point temperature first. But in order to get the bubble point pressure, there's no problem. The answer is straightforward according to this one, right? And then you just play Dalton's law and Law's law. You will get the rest of the unknowns, such as molar fraction and the partial pressure. Okay? Okay, so next one is dew point temperature and pressure. What's dew point temperature and pressure? So the dew point temperature of a gas may be found using the method of similar that for bubble point temperature estimation. Okay, so let's use your imagination. This is there are many species in the gas phase. There is no liquid, and then you start to decrease the temperature. So the bubble will condense. One droplet will condense. So again, if you're talking about dew point temperature, you have to keep the pressure as a constant. So this is initial condition. You know this. So a gas phase contains the condensable components A, B, C, blah, 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 and the non-condensable components G, okay, as a fixed pressure P. So if the gas mixture is cooled slowly to its dew point, T dP, it will be in equilibrium with the first liquid that forms. So A, B, C, D here, you decrease temperature, you get a first drop, you get a first droplet. So this is known, right? This is unknown. So you want to find out this. So assume the Law's law is applied. The liquid phase rules molar fractions may be calculated as what? As this one. So in order to get the dew point temperature and pressure, this is the equation you need to remember. What is this equation? Professor, what is this equation? Law's law. Law's law, right? So how do you do that? Again, for all the dew point temperature, you need to do try and error. Try and error, okay? Wait a moment. Right. So at the dew point of the gas mixture, the molar fraction of liquid components must sum to 1. So this one, XA, XB, XC, XD is equal to 1. YA, YB, YC, YD equal to 1, right? So, ladies and gentlemen, please remember you have to use this XA, XB, SC equal to 1. This one. And then you use Law's law to replace XI. So you'll get something like this. You'll get something like this. Because this is known, right? P is initial condition. This is pressure as a constant. Yi is the initial condition. You know this. You know Yi. You know this one. You know this one. What you don't know is this one. Right? What you don't know is T dP. And if you find out dTp, you will know PA star. Okay? And you add up this A, B, C, D spaces, that will be equal to 1. So what you need to find out is dTdP by try and error. For example, 80 Celsius. You find 80 Celsius, the vapor pressure of A species at 80. You find out B species, vapor pressure of B species at 80 Celsius. You find out vapor pressure of C species at 80 Celsius. And you put the number in here, and you get this at 1, then you got the answer. But if it's not equal to 1, try again. I'll give you an example very soon, okay? How about dew point temperature? Dew point temperature, again, is the same thing. Okay, you put this here, and then, so this is dew point temperature, right? Okay, so you do this, and when the value of dTp can be found by trial and error, once the expression for vapor pressure of dTp has been substituted. Okay, so the composition, so once you get a temperature, how can you get this? How can you get XA, XB, XD? Again, Law's law. So you know this, you know this, you know this, of course you know this. And how about the dew point pressure? Again, that same thing. So if you increase the pressure, you will get the first drop of the liquid come out. And again, you use this equation to find out the answer. And the easy thing is that because the temperature keeps as a constant, so you know the temperature. You know this one. You know this one. You know this one. All you don't know is this pressure, right? And this is easy because you take this out. You know YA, YB, YC, YD. So equal to 1, then it will be easy for you to calculate the dew point pressure. So in order to get dew point pressure is easy, but it's not easy to get the dew point temperature because you need to use trial and error method. Okay? So please do the practice by yourself. We are going to have an example soon. Okay? So this one is that you want to get, once you get the pressure and you want to get the this molar fraction, is easy because you know this, you know this, you know this. So this is the example I want to show you, and I want you to work with me because this is very important. So example 6.4-3, bubble and dew point calculations. So assume you have two species only. So I want you to calculate the temperature and the composition of a vapor in the equilibrium with a liquid that is 40% benzene and 60% toluene at 1 atm. So this information telling you that in the liquid you have 40% benzene, which is molar fraction, right? 60% molar fraction is 0.6 and 1 atm. So you keep the pressure as a constant. So is this calculated temperature a bubble point or a dew point temperature? Which one? Of course, it's a bubble, right? Because you have all the liquid. Because a liquid at 40 benzene and 40 toluene. So you have all the liquids. So what you want to calculate is what? Bubble point temperature, because you keep the pressure as a constant. So at this moment, you have 1 atm here, and then you increase the temperature, and the first bubble come out. Okay? And you want to find out the composition of this bubble. So because we only have two species, that means YA and YB. So YB can be 1 minus YA, right? So actually you just have you only have two unknowns. This one, temperature, and YA or YB. So how can you do that? So let's set A as a benzene, B as a toluene. So remember that if we want to do the bubble point, we have to add up all the partial pressure together to become total pressure, because total pressure is 1. This is initial condition, right? 1 equal to partial pressure, molar fraction of total pressure, right? Okay? No problem. And then what happened? You put this YA to become Dalton's law, right? This one become Dalton's law. This is Dalton's law. Sorry, Law's law, Dalton's law, right? Law's law. So you move this to Law's law. Replace this to Law's law. And then what you don't know is this one. So you need to do the trial and error. So you put XA becomes 0.64 and XB 0.6, and because total pressure is minus 760 millimeter mercury equal to 0, sorry. So now you want to do trial and error of TBP. So choose a temperature to evaluate vapor pressure A, vapor pressure B for the temperature from the Anton equation using constants from the table B4. Use trial and error to let this close to 0. Okay, let's do it together. So this is the equation here. And we want to, in your final exam, I will give you a start point. I will say that start from 95 Celsius. Okay, for example, start from 95 Celsius or start from 80, or the range is from 80 to 100. So I will give you a range, and you start to do a trial and error. Bring your calculator, okay? Bring your calculator. So I will give you this equation, and of course you need to find out this equation by yourself. So in the very beginning, it's 0.4 Pa, 0.6 Pb minus 760 millimeter mercury, and you need to get this answer. So, and you need to know this is benzene, right? Benzene, and benzene is here. Okay, benzene is here, and I make it large. The benzene temperature AB, this is ABC, and the constant ABC is applied in the range, temperature range at 14.5 to 80.9. Okay, and you can find out Tulane here. Tulane is somewhere around here. Okay, so you can put Tulane or ABC here. So you put this. So first of all, you set up at 80 first. So if at 80, that means what? This is 80, right? Remember the unit, 80 here. So you put A 6.89 here. You put B 1203 here. And C is 219 here. And temperature is here. And you got this one. Okay? And then you will get this BP. You know, it takes time. So I want you to practice before you really take your exam. So you will make your speed faster. Don't waste your time when you do your exam. Okay, and then so once you get PA and PA star and PB star, you put this PA star and PB star here. So and then minus 760 millimeter mercury, you can get this. You can get this is minus 282.2. Obviously, this is not equal to 0, right? Okay. So I tell you that I might give you a range from 80 to 100. So you put another 100, and you got an answer here. You put, again, ABC is constant. You just put a 100 here, and you got P star. P star A, P star, PA star, and PB star. And if you do the calculation here, you got this 100 is this is about 113.99. Obviously, this is not equal to 0. So you know you get a 1 minus 1 negative, 1 positive. So obviously, you know the right answer will be between 80 to 100. So it might be close to what? If this is linear, for example, if this is linear, this will be close to 100, right? So let's set up you don't need to set it like this. You can set up at 95 or 93 if you want to. But our book tells us that they set up at 94.25. So you put the 94.25 here, and you got PA star and PB star. Of course, you will get the answer, which is minus 19.68, which is very close to the right answer, right? And then you are not happy. So you know that the true answer, the more approach to the true answer will be between 100 to 94. So you choose 95. And you put a 95 here, and you got minus 1.08. So it's very close already. So for your exam, in your midterm, in your final exam, if you can do this for me, I'll be more than happy. Okay, I think I will give you a point already. Okay, so, and then you do it again, 95.14. And in the end, you think is very close to the 0, then this is the answer, 95.14. So 95.14 is dew point. Sorry, 95.14 is bubble point. Temperature always try and error, okay? Right, so 95.14 is the bubble point. Okay, and then what happened? What do you want to get? So you get this answer. So you get this answer here. And now you want to know the molar fraction in gas phase. So according to Law's law, you know that you have this already. This is none. And XA is initial condition, right? So PA you will know. YA you will know. Okay? So please place around so you know that. So you know partial pressure A, partial pressure B, and of course these two get together will be 760 total pressure. And you know the YA, and you know the YB. Okay? Right. It might be, let's practice one more. So since the composition of liquid was given, this was a bubble point calculation, right? Okay, let's practice one more. The calculation of temperature and the composition of a liquid in equilibrium with a gas mixture containing 10% benzene and 10% toluene, and together with balanced nitrogen, which is 80%, right? At 1 atm. 1 atm means what? Again, this is keep it as a pressure is a constant. So we are going to talk about dew point. So is the calculation temperature a bubble point or dew point? Because you have composition in gas phase, of course, you want to calculate the dew point, right? Dew point. So here you have A, benzene, B, toluene, and together mixed with nitrogen. And in the gas phase, you have 10% A, 10% B. The rest of them are 80% nitrogen, right? So temperature is 1 atm. And then if you decrease the temperature, you will get one droplet. And then in order to find the composition of droplet, you need to use try and error because you want to calculate the temperature, right? Right. Again, you just play around Dalton's law and the Law's law. So from the equation, I hope you still remember that if you want to do the dew point, you have to put the molar fraction in liquid together. Remember that? You put XA, XB, XC, XD become 1. And you follow the Law's law equation, you can replace XA to become this, XB become this, XC become this. And since you only have 2 components, you just put the equation like this. And then when we talk about temperature, you always use try and error first. So this is try and error. Try and error. Right. So because you know YA is 0.1, YB is 0.1, and the constant pressure is 760. So this is -1. So all you don't know is this one and this one. And again, try and error. So I move this equation to this one, to here. And let's do the try and error first. Try and error similar to part 1. So in the end, you will get 52.4. If you put a 52.4 here, use Dalton's Anton equation, you will get this. Anton equation, you'll get this. Okay? So the solution is taken to be 52.4 Celsius. So once you know this temperature here, and now it's time to know the molar fraction in liquid phase. So how can you get that? Again, you play around with this. So because you know the total pressure, you know this one, right? You know this one. And you know this one, of course you will get this one. Right? Okay? So easy. Once you know how to, you know the skill. If you know the skill, that's easy for, and after that, well, that'll be easy. Okay, please do this by yourself. Right. The question 3 is that a gas mixture consists of the 15% benzene, 10% toluene, and the 75% nitrogen is compressed isothermally. Isothermally means what? Temperature is as a constant at 80 Celsius. So 80 is a constant until the condensation occurred. What's the pressure will condense begin? What will be the composition of the initial condensate? So the important thing is that you know this is initial condition. You know that in the gas phase you have 15% A, benzene, 10% toluene, and 75% nitrogen. Right? This is right in the beginning. And then the temperature is as a constant. So you don't know the pressure. Okay? Pressure is unknown. And then once you increase the pressure, and the first drop will come out. First droplet will come out. And you want to find out the composition of A and B. Okay? So how are we going to do this? Again, I tell you that once we want to know in the liquid phase, then we need to add up this A and B together, right? Equal to 1. So let's put this equation. A and B together and the Law's law equal to 1. And because you know that the temperature keep as a constant, so you know the temperature is 80 Celsius. So you use the Anthony's equation, put it here and here. Anthony's equation, put it here and here. So you get the total pressure. So you know the dew point pressure by this simple calculation. Once you find out the vapor pressure of A and vapor pressure of B, vapor pressure of benzene, vapor pressure of toluene. Okay, and then so put this in and you get the answer. Ladies and gentlemen, please work by yourself. Do this by yourself. And how are you going to get this molar fraction? Law's law, right? Okay, I think I don't work out this with you together, but I want you to do the practice at home by yourself. When you want to do the dew point and bubble point pressure, that's easy because you can straightforward to get the answer. But once you want to know the dew point temperature and dew point bubble point temperature, you need to try and error, do the try and error method. Okay? Right. So I want to read the summary for you on Wednesday because I summarized how to do the calculation, the method. So I want you to remember this. So I want to move to the 6.4D today. Right. You might wonder that, Professor, try and error or calculation is menokusai, right? Menokusai. Do you know what I mean? It's troublesome, right? It's Japanese. Anyway, it's troublesome. Do we have easy way to get the answer? Yes, this is the easy way to get an answer. But of course, you don't dealing with this case using you don't dealing with complicated mixtures using this case. This is only for 2 components only. So you have 2 components. You don't have component B, component C, component D. Then That's not. This is not the case. Okay. So this is called graphical representation. Graphical representation means that there are different. You can use graph figures to find out the answer, and which is relatively easy. So for the binary system means only two. You have A species and B species only. You don't have others. Right. So you use a diagram. Means that if you want to do the dew point, that means you keep the pressure as constant. If you're doing the pressure, dew point pressure, you make the temperature constant. So you have PXY diagram, which is constant pressure. You have TXY, a PSY diagram, which is constant at a constant temperature. Okay, so how are we going to do that? This is very easy. So, for example, the previous example we use benzene and toluene, right? Benzene and toluene. So we use the benzene and toluene as an example. Benzene and toluene here, you have different pressure and different temperature. So obviously, you understand you have different molar fraction in the liquid phase and the gas phase. So this is Tx, the temperature XY diagram at 1 atm, because we need to keep this diagram as a constant pressure. So this is TXY diagram. And this is the vapor curve. This is vapor curve and liquid curve. Okay, this is the molar fraction of benzene. And this is temperature. There's no, you might ask, where is pressure? Pressure is 1 atm as a constant. Okay? So, and then, this, if I address this as 0.4, so why is 0.4? Is this the composition in gas phase of benzene or liquid phase of the benzene? For both. I'm going to tell you why. Okay, in the very soon. Okay, so if we increase the temperature, go up here and meet this point, this is bubble point, right? Because this region is all liquid. And increase the temperature here and then bubble point. And go up to here, this is the vapor region of vapor and liquid mixture. If we go up here, this is all vapor phase, right? Vapor phase. So if you decrease the temperature, this is called dew point. So either you want to know the bubble point or dew point. Okay. And PXY is you keep the temperature at 1 atm. 100 Celsius. Again, liquid region, vapor region, and liquid and vapor region mixture. Region for liquid and vapor mixture. So again, this Y is for the molar fraction of the benzene. Can be XA in the liquid phase, can be YA in the gas phase. Okay, so so again, increase the pressure, this is called dew point. Decrease the pressure, this is called bubble point. Okay. So there are some explanation TXY. So for a fixed pressure is fixed, right? At least in this graph is 1 atm. If you have 2 atm, this graph will change. Okay, so especially we just focus on 1 atm here. So a plot of the equilibrium temperature versus the molar fractions of the one of the component. Because this is binary, right? So you can have benzene or toluene as the fraction here. So normally we use more volatile one. Benzene is more volatile, has a higher volatility compared to toluene. So you use benzene here. And then this benzene here. So the curve for both liquid phase and the vapor phase, I just mentioned this to you. So T versus XA or T versus YA. Okay, but you all address to the A. A is benzene. So several values of the XA and the equilibrium vapor component YA is determined for each liquid components. You might don't know how to do this, so let's practice now. So bubble point and temperature calculation. How do you do the calculation of bubble point temperature? try and error in the previous case, right? Okay, but now we have a graph to let us know rather than calculation. We use graph to tell us what is the bubble point. So this we have constant pressure. We have the initial condition, which is we know the molar fraction of XA and XB. Of course, we increase the temperature, and we got the first bubble, right? And then bubble point for a given liquid composition at a constant pressure P, and we have something like this. I show you in your final exam. I give you this graph. I give you this diagram, and I tell you that. Okay, this is X benzene. This is initial condition, right? Initial condition. This is X benzene. So assume we have 0.5 here. So go to the liquid curve on the TXY diagrams for the system pressure and read the desired temperature from the ordinate scale TBP. What does this mean? If I have X, let's say 50 at liquid phase, and then I increase the temperature from here 70, 80, 50, 85, 90, and hit this curve here. And if you move this curve from the right to the left parallelly, okay, you got what? This is the bubble point. Wow, excellent. Rather than try and error, you can get it very easily. But of course, this is limited cases, which is only for binary components, right? So this is bubble point. Okay, then so you solve the problem of the bubble point here. Okay, so your temperature is known. And how are you going to realize the molar fraction in gas phase? So move horizontally to the vapor curve to determine the composition of the vapor in equilibrium with the given liquid at a temperature YBN. So what does that mean? Move this horizontally to vapor curve, and you will realize this is Y molar fraction of the benzene, which is 0.7. If this is 0.7, this will be 0.3, right? Okay, so with this graph, wonderful. Rather than do a lot of calculation, you will realize how easy is this. But of course, this is a not precise answer, right? This is roughly rough answer. So how about dew point temperature calculation? Previous one, this is bubble point, right? How about dew point? Dew point is that you keep the temperature pressure as a constant, and then you know the initial condition of in the gas phase, and then you decrease the temperature, and you got a first droplet. Sorry, you got a first droplet. This is called dew point. And of course, you want to know the dew point temperature. You want to know the molar fraction in liquid phase. So here, again, we show you this one, the same graph, and the pressure at 1 atm. So the dew point of a vapor mixture for A and B at P, which is a constant, right, can be determined from the TXY diagram if there is no species then other than A and B in the gas phase. Again, this is benzene to them. Okay, this is benzene to them, right? So you have benzene at the vapor phase XYA, and then read the dew point temperature TB from the corresponding coordinate values of the vapor curve. So for example, if I have, again, instead of X benzene, and now we use Y benzene here. Again, it's 50, 0.5. So now we want to know the dew point, right? We want to know dew point. So you go to the line here, meet the vapor curve, and this is what we call dew point. In the previous page, this is bubble point, right? And now you go up here, this is dew point. So you know the dew point temperature. And what you need to know next is the molar fractions in liquid phase. So I'm sure you know that how do you get the molar fraction in liquid phase? Horizontally, and this one drop, right? This is the molar fraction. Let's say 0.2827, right? Benzene will be 0.27, and that will be 0.72, right? 73. Okay? Easy. Right. So dew point temperature and calculations is that there's no species rather than A and B. So if a condensation species is presented in the gas phase, however, you must use this equation. So it's only for binary condition, a binary system, okay? Binary component system. Otherwise, you use Law's law and Henry's law to solve the problem. So here is the example. Please give me another 5 minutes. Let's finish this example first. So example is that a liquid mixture continues to vaporize. That's that 50 mole benzene and 45 mole Toluene liquid mixture system at a fixed pressure at 1 atm. So the liquid is 50%, 55%, 45%, right? And you keep a temperature as a constant, 1 atm, and then you increase the temperature. And then you get the first bubble. So these two, temperature and the composition of in the liquid in a bubble in a gas phase, molar fraction. So how can you do this for me? In liquid, right? So let's say benzene is 55, so it's 0.4, 0.5, and before 0.5 to 0. Somewhere in the middle here, right? So if you want to do this, 0.5 benzene here, 0.55, right? And then you go up here, you hit this place or this place, because we are talking about bubble point. So this is bubble, right? The first one, you hit this here. So it tell you what, the bubble point is what, somewhere 80, 89 or 88, right? This is called bubble point. Wow, 90. Anyway, it's almost the same. And then the composition here is what? You move this horizontally here and drop, let's say 77, 0.77. Yes, I'm right, right? 77%. So instead of do the calculation, you get these two already. If I ask you partial pressure, can you get it for me? Yes, you can. Dalton's law, right? Okay, so the other question is that once a small amount of liquid has been vaporized, the remainder of no longer contain 55 benzenes. It contains less since the vapor pressure is relatively rich in these components. So if we increase the temperature from 90 to 100, if we increase the what? The composition decrease, right? The benzene decrease. See that? If we increase the temperature, the composition keep on decrease, right? So you know the relationship between this temperature and the composition of benzene. So the temperature of the system steadily rises as more and more liquid is vaporized, and the composition of the both phases change continuously during the process. That's no doubt. Right. And how about vapor point? So again, there are 40, 60, right? So the Toluene mixture there, 1 atm. If the mixture is steady vaporized until the remaining liquid contains 25% benzene, what's the final temperature? So first of all, we need to know the dew point first. So again, the 40% benzene is here, right? So where you need to see is here or here, because this is bubble point, right? So you need to know that 0.4, 0.6, and keep on temperature, and then you increase the temperature. So first of all, you have composition of benzene. Benzene here is what? It's 0.4 here. And then what's the bubble point? You go up here, bubble point, right? Bubble point. Bubble point, let's say 95. Just that's what we know, right? And benzene is what? Benzene is here. What's the number? 62, for example. 62. Okay. And then now I want to tell you that if this liquid contains 25% benzene, that means what? This is only 25. So what's the final temperature? If this reaches 25, then the temperature will be what? 100. Okay? Because I keep on increasing the temperature, right? Temperature will be 100, and YB will be what? You go up here, that will be 45, 0.45. Okay? Right. Please work with me. Last one. Okay, the bubble point and dew point calculation. Again, if you have 40 at 1 atm, and this is the gas, right? The gas 0.4, 0.6, that means what? That means you have first drop. You want to know the benzene here and toluene here. So again, you write down the benzene because this is dew point. So you need to calculate from 0.4 here and then go up to here, right? And this is what? 102, for example. So the bubble point is 102, and then this one will be concentration of the benzene, which is 0.2. Okay, and next is the condensation process until the remaining vapor containing 60%. So I keep on dropping the temperature. So the contains 60% vapor benzene. So 60%, where is 60? Here, right? So what's the final temperature? 0.6, and you go up here. And the final temperature will be 96, right? And the concentration will be what? Will be, say, 0.38. Okay, so these are the answer. Right, okay. So I think this is the example for you to know that. I'm sorry to delay for 7 minutes. So apologize for this. I hope you catch the point today, because the material you want to digest is a lot today. So I want you to go home and practice, and very important for the final exam. Okay.